Great. So hi, everybody. Welcome to today's AFMS seminar. My pleasure to introduce our speaker for today, Dr. Jean Rabault from the Norwegian Meteorological Institute. He works a lot on machine learning applications to meteorology and the study of the Arctic. And he also has a long-standing interest in deep reinforcement learning and its application to active flow control. And he's going to be talking a bit about that topic today. So please take it ahead, Jean.
Yes, thank you very much for the introduction. It's very nice to be able to present today. So as you say, I'm going to present today about deep reinforcement learning for active flow control, which is an activity and nowadays a side project I've had for quite a years. So a few words about the motivation. Flow control is a relevant theoretical and industrial problem because it can be applied to many processes, but at the same time, the time dependence, non-linearity, and high dimensionality that is involved in flow control often break the tools we have to design control laws. So often methods based on linearization do not work very well, and it's a field that has been active for a long time, but I think it's famously difficult to come with effective non-trivial control strategies. So when you are met with this challenge, of course, one can either try to push further methods that already exist or to take into use new methods. And personally, I've been interested in taking it to use new tools, and in particular, deep reinforcement learning. And deep reinforcement learning is, I will talk much more about it when I explain the methodology, but basically it has been very effective on control problems for very complex systems like Go, Poker, robotics, which is like interaction with nonlinear, high dimensionality complex systems. A few words about the agenda. I will start with a short introduction to artificial neural networks and supervised learning. Then I will explain how it's possible to go from supervised learning to reinforcement learning. And then I will talk about deep reinforcement learning for active flow control. Okay, so first, a short reminder about artificial neural network and supervised learning. So artificial neural networks are simply a set of neurons. Maybe you've heard about it because it has become more and more common to talk about it these days. And basically a neuron is just doing a weighted input, a weighted sum of its inputs, and then applying an activation function on top of it. So simple computational units. You can organize them in layers, and then each layer feed into the following layer, and so on and so on. And you can, if you want, have some more complex layer, like this convolutional layer, which just applies the same convolution kernel everywhere on your image, for example. So it's just one of the many examples, and you can have more and more refinement in how the neural network is defined. So why is the paradigm of artificial neural network interesting? Is because depending on what activation function you use, you can reproduce very broad classes of functions with a neural network. So if you use a linear activation function, you're just doing a linear function of a weighted sum of inputs. So everything is linear. So it's kind of boring. But as soon as you use a nonlinear function, then you can get into much richer dynamics. So there are many kinds of nonlinear functions. You may hear about it in the literature. In practice, nowadays, what is called rectified linear unit, or ReLU, is very often used because it works well. Some people see it as maybe the best alternative we are out there. But the key result is that if you have a deep neural network and a nonlinear activation function, then you have what is called a universal approximator. So it means given any function, if your neural network is big enough and if you manage to train it, you should be able to be epsilon close to the initial function. It's a result of density of functional spaces into each other's. And this is known for a long time. There is this paper since at least 1989 that proves this result for wide classes of activation function. So now that you know that neural network can be a universal approximator, the question is what kind of architecture, how should you build your neural network? And
really?
Hello? And in theory, a one layer is enough to be a universal approximator. In practice, you can take advantage of depth invariance by translation and so on to build a neural network that is more adapted to the specific task you look at. So there is this canonical example, which is a XOR function. If you want to compute the XOR for n inputs, you would need of the order 2 to the power of n neuron if you use only one layer, but you can use only n neurons if you are log n layers. So an illustration of this architecture importance. Okay, so now that you know that it's universal approximator, you can be effective in representative functions, how to train your neural network, so how to basically adapt it so that it matches a function that you know empirically from data. Here, we are lucky because there is this simple method of gradient descent / backpropagation of error. So the idea is very simple, is that you feed data into your network, you make the data propagate until the end of your network, and then you can compare the output of your network to the label, to the ground truth you should reproduce. And you can backpropagate this error by the Leibniz rule to fill the sensitivity of the output of the neural network to all the parameters which are typically the coefficients in the weighted sum. And this way you can do a gradient descent to train or tune your network to reproduce exactly the function that is shown in the data. And it's a wide field to talk about those supervised learning, but just to summarize, today I think supervised learnings work very well on many examples, like image analysis, some speech recognition, and so on, works very well. So we are effectively able to learn whatever function we want in an effective way. So when you have supervised learning, to repeat myself, what you do is that given a function that you know from examples, so sets of labels, sets of predictors, so for example 10 values, and then labels, so the one value you want your function to reproduce as label is equal to function of predictor, you can train a neural network to be arbitrarily close to it. But of course, it means you can only reproduce functions you already know, right? So if you have many examples of image classification, you can reproduce this with a neural network. It's really helpful because very often there are these functions that we know empirically because we know how to classify bananas from cup of tea, but we don't know how to express it in an analytical way. This is typically what we can do with supervised learning. But what we want to do for flow control is a bit different because we want to find out a function that we don't know in advance, right? Because we don't know the control strategy that is going to work. And what I'm going to explain now is a bit what kind of algorithms you can use in order to go from supervised learning to reinforcement learning. So reinforcement learning, really learning a function you don't know in advance. So if you want to learn something that you do not know in advance and you want to be data-driven, then there is not 1 million possibilities. You more or less have to learn by trial and error. So it's this classical framework that is often shown in papers, in introductions. Basically, you will have an environment, and the environment is kind of the plant or the system you're trying to control. And you have the agent, which is the reinforcement learning part. And then there is interaction between the agent and the environment through 3 channels of communication. So at each time step, the agent can observe the state of the environment. Based on this state, take a decision about what action should be taken, apply the action of the environment on the environment. The environment will have its own dynamics and advance in time, and then the environment will return a reward value that says how satisfied you are with its new state. And in this framework, everything is actually stochastic. So the environment can have stochastic dynamics like Markov chains, and the observed state can be have stochasticity in it and be only partial. You don't need to observe the full system, and so on and so on. So it's very applicable to real world. And to introduce a bit of notation, I will call S the state, A the action, R the reward, and the policy by A knowing S is how you define the probability that you should take action A when you are in state S. And this can be also stochastic. So there are several methods to perform reinforcement learning. So the boundaries are sometimes a bit unclear in between them. The main ones are Q-learning and policy gradient. And what I will do now is give you a very quick introduction of Q-learning and policy gradient, just so that you feel a bit how these methods work. And yes, to put in a bit of context, we are looking at one specific method into this big tree of machine learning techniques, right? So I said a few words about supervised learning, and we'll use it as a tool. We will focus on reinforcement learning, even if there would be even another thing that is unsupervised learning. And then we are looking in reinforcement learning at a class of problems that is model-free reinforcement learning, because we don't have a close analytical model of the environment. We only interact directly with the environment. And then there are those different categories of reinforcement learning techniques. Okay, so a few words about Q-learning to help you to understand how Q-learning really works. So I think the renewed interest for Q-learning is this paper from 2015, but it's actually based on much older ideas that are known under different names, like Q-learning or dynamic programming is also a way it's often called. So the idea is, you know that you get this reward each time you have interacted with this environment. So first thing is that you don't want to optimize only the instantaneous reward. You want to optimize the instantaneous reward plus the reward in the future, and so on and so on. So you will introduce a discounted future reward, this big RT, which is small RT, so the instantaneous reward, plus gamma times RT plus 1, the reward at the next step, plus, and so on. So gamma is this discount factor, typically 0.99 or 0.95 or something like this. That says how much better you like a reward now in the present compared to a reward in the future. And what this says is that by optimizing this reward value, you will actually try to optimize not just the state in the present state, but the state also in the future states. Okay, so what we want to optimize is this value function v pi of s, which is the expected value of the sum of this gamma t rt. So it's the expected value of this discounted future reward, and it is this expected value knowing that you start in the state s, and then from now on you decide what action you will take by following the policy pi that tells to you what action you should take. And then we can introduce the optimal value function, this v star, which is a max of all policies of v pi. So what we want is to find the policy pi really that maximizes this value and give you v star. Okay, so in order to do so in Q-learning, you traditionally introduce something that is the expected return, this Q function, starting in state S, performing first the action A, and then continuing with the policy pi. So this Q pi SA. Then if you do a tiny bit of notation, you will find that Q star, it's the maximum of all policies of Q pi, and V star is the maximum of all possible action you can take at the present step of this Q star. And by there, you can reverse your formula and say that your optimal policy is the argmax of this Q star function. So basically, all we are saying is that the optimal, if you find the optimal Q function corresponding to the optimal policy, what you should do is first take the best action possible and then continue with this policy that gives you the best action possible. So it means, that's a bit of notation, but basically it just means that knowledge of Q star is knowledge of pi star. And we are lucky because there is this equation known as the Bellman equation that allows us to iteratively approximate Q star. So if you apply this formula, which is Q star is equal to R plus gamma maximum and all action of Q star, so it's an update rule, then your Q star will converge to the real Q star in a sense. Or okay, this equation is verified for the true Q star, and then you can define an iterative rule to approximate it. That's the thing that is under. And this is known as dynamic programming. So basically what you do is that you break your problem into first taking the best action you can on the long term and then following the policy with the best actions. If you're not familiar to it, you need to wrap your head and go through it a couple of times to convince you of it. But basically, the way to understand how this works is that this is a bit like exploring a maze. Like if you start from a given place and then you want to explore a maze, you have no choice but you take kind of random actions. And sometimes you will get a good value of the reward, sometimes you get a bad value of the reward, but the idea is you can make this reward diffuse back. Like when you are at a location and you know going to the right makes you die, you can say that there is a very negative quality of this action of going right from this place. And you can make it diffuse again and again and again. So until you build kind of a map of the full environment that says, okay, for each state, what is a good decision to take? Of course, this kind of approach, you imagine immediately how it can be applied for a word that is kind of a matrix, right? I mean, this is the example of the maze. You could just discretize it in the matrix and fill all your values. But of course, the word is nonlinear, high dimensionality, and complex, so you cannot really represent everything by like a kind of discrete set of states and put it in a big matrix. So the solution, a possible solution there is to replace what would be kind of a state-based, like tabular-like description of the word with a universal function approximator. And we know that we have this effective universal function approximator that is a neural network. And this is the idea behind deep Q learning, is that you use a neural network in order to represent, parameterize this Q value. So what you do basically is that you parameterize Q as Q of state, action, and theta I, where the big theta I is a set of weights of the neural network. You don't really want to take an Rmax of a neural network. So instead, you can discretize the different actions you can take as output, different output of your Q value and outputting the quality for each of them. And then instead of having this iterative update rule, you have a loss function in the case of a neural network that just reproduces this update rule. So basically saying that you have this mismatch of the Bellman equation and you want to reduce it, to converge to it. There are a few more tricks, like for example, you want to take advantage of the data in an effective way. So typically you take the data you have gathered, you put it in what is called an experience replay buffer so that you can learn from it several times by shuffling it. There is also something about how you update the target for Q, technical details. But basically when you implement all of this, you get an algorithm that allows computer to learn by trial and error, not only for trivial systems like tabular-like systems, but also for systems that are nonlinear and complex. And you can either learn directly in the system, or you can even, if you want, have different actors that fight each other in an adversarial way. So yeah, and what I want to say here is that this deep Q learning uses artificial neural network, but of course the neural network is not the fundamental part here. The neural network is just used as a functional approximator. You could use another functional approximator. It just neural networks work well in practice. So this is the main idea behind Q learning, saying basically you explore the world and you make good or bad action quality diffuse back into your kind of dynamic model, similar to dynamic programming. The other big category of methods for doing deep reinforcement learning nowadays is this policy gradient method. So the aim of the policy gradient method is to directly learn the policy pi. And just to remind you, the policy pi AS describes the probability that you should take the action A given that you are in the state S. And for the policy gradient, we consider this policy as something stochastic, so a kind of distribution that for each state is parameterized by the neural network. So basically, what happens is that you give the state input to a neural network, and the neural network will use this to generate typically the mean and the standard deviation of a Gaussian law. And then you get a distribution saying, okay, the optimal policy would be to follow this distribution of actions. And then, of course, So of course, if your system is bounded, you will use not a Gaussian law, but something with a compact support. But that's small details, and you can use other kind of probability density functions. Basically, what you can do then is that by tuning your neural network, you can shift the mean of the distribution. You can make it more spiky in a sense, so you can control really which kind of action you take. So this is the full idea. You train by shifting the distribution when you train the neural network. And the neural network, same as last time, it's parameterized with a set of weights theta I, and it decides these parameters in your law. So the objective then is to find the set theta of weights of the neural network so that you maximize the expected value of the discounted reward. To give you a bit of understanding about how this algorithm works, typically you solve this problem by defining tau, that is a state action sequence. So saying that you transition from state 0, taking action 0, that makes you go to state 1, action 1, state 2, action 2, and so on and so on. So this has realizations of the trajectories in the phase space in a sense. And then you can see that the value that you get following the policy pi with a set of weights theta, it's this sum over all the possible trajectories in the phase space of the probability of taking this trajectory tau, given that you have the set of weights theta that decides the distribution of your actions, times the discounted reward associated with this full trajectory. And then what we want is just to maximize this value function. So you can take the gradient respective to the weights of the neural network set of weights theta of v theta. And you can do a bit of mathematics, introduce a classical gradient trick, and then come to this sum over all the trajectories, so sum over theta, of probability to follow this trajectory. Sorry, I was saying theta, but tau. It's a bit early in the morning. Sum over all the trajectories, tau, of the probability of following this trajectory tau, knowing the set of weights theta, times this gradient of the log probability, times this reward, so this last line here. And what is very nice for it is that you see there is a sum of a trajectory of the probability of the trajectory times a big term. So of course, this looks like a Monte Carlo method, right? And you can estimate it by doing m rollouts of your trajectory in the phase space under control by the neural network as 1 over the number m of rollouts times the sum over m of this big term gradient theta of the log of the probability times reward. So to understand this a tiny bit, what does this mean? It means that the gradient respective to theta of the value function follows this bin function. And what this means in practice that we try to tune the neural network so that we increase the probability of following good trajectories and we reduce the trajectory of following bad trajectories. So this is kind of the idea behind it. And what do we miss here in order to be able to actually implement it in practice? Well, we are able to do m rollouts by interacting with the agents, with the environment. That's not a problem. We know the reward over the trajectory because we can compute it based on the instantaneous reward. The only terms that we miss is this gradient theta of the log of the probability of the trajectory. Just to illustrate a tiny bit, it's quite easy to compute because you can play a bit around with the mathematics, and gradient relative to theta of log probability, it's the gradient relative to theta. What is the probability to actually follow this trajectory? It's the product of the probability of transitioning from state st to state st plus 1, knowing that you take the action at, time the probability to take the action at when you are actually in the state st. And then you can do the classical log algebra thing, and you can observe that this first term, the sum of the log of the probability to transition from state st to st plus 1 when you take action at, this is actually not something that depends on the policy, right? Because this is just the own dynamics of the system. So this term disappears, and you're only left with the sum, with the gradient over theta of the sum of the log of the pi theta. And this is something that is purely defined by your network. So this is something that you can express by this kind of backpropagation of gradients, find the sensitivity of this log pi to every one of the data. So basically, if you put everything together, you get an algorithm where you do rollouts, so basically trajectories in the phase space and interaction with your system to compute the gradient with respect to the weight of the neural network of this value function. And the term that you have, this gradient of the log of the probability, you can express it from some gradient estimates on your neural network. Yeah, so it's a bit of notation. If you're particularly interested in it and you want to understand a bit more the details, you probably need to go through it a couple of times and think about it, but it's not really very complicated. Of course, it's possible to do more advanced algorithms based on this idea. One of them, for example, that I will talk about later on in the talk is this proximal policy optimization, PPO. And the idea is that you implement tricks on top of tricks in order to make it work better. Like, for example, in the PPO, you actually have two neural networks. You have a critic network that learns the actual reward estimate, because it's not so trivial to know, given a given state, what is the actual discounted future or actualized reward that you will get over the full trajectories, because it depends not only on this state, but also on the probability to take all the states in the future. So you have this critic network that learns this with a Bellman equation in some Q-learning way of doing. And then in parallel to it, or like working together, you have the policy network that is actually using a policy gradient. Then in addition, in the case of PPO, you try to discourage very big updates that could come from a lucky roll. So you clip the gradients in order to make sure your learning is a bit stable. So there are quite many complex and a bit tricky things to implement to make it work right in practice. So I would personally, but maybe you disagree or some people disagree, but I would personally think that it's a bit lot of work and a bit risky to try to implement those things yourself. But luckily, there are some good open source frameworks for using reinforcement learning. A few ones are TensorForce, even if the development is discontinued now, Stable Baseline and Tianshu that are still very active. And when you use this open source framework, the workflow is always the same and it's very simple. You have to build your application-specific environment by filling a class. So basically, if you want to control a CFD simulation, you have to wrap your CFD simulation in a bit of standard APIs so that this framework knows how to implement with it. Then you just implement the agent from any of this framework, and you just run a small script in order to train. And by training, you learn how to control the system. And once you know how to control the system, you can evaluate the control policies that you've been applying in a deterministic mode. There are some frameworks for coupling specifically deep reinforcement learning with fluid mechanics. One I've been a tiny bit involved in is this DRL in fluids, for example, that couples Tianshu or Stable Baseline or TensorForce to some open form simulation. And I will also give links to more example codes in the following slides. A few words, I've been talking quickly now about training versus deterministic. The idea is that when you want to train your neural network, then you have to explore your system. So you have to not only follow the policy, but also maybe take a bit of random action to try to see states that you would not see otherwise. And this means usually sampling from the policy distribution instead of just taking the maximal, most likely action, for example, and or adding some random noise to the action that is actually taken. So therefore, when you perform training, you will see that your curves always look a bit messy and there is a bit of noise on everything. This is this exploration process that takes place. But once you have finished with training, you can apply your reinforcement learning agent in what is called the deterministic mode. And then what you will do is that you will just pick the best action you think you can pick at every step. And this will provide you a much smoother control law and give you like the nice smooth policy application you need. Okay, so this was a bit of introduction. it's very fast to go through it, but I think it's important to understand a bit how those reinforcement learnings algorithms work in the main lines, so that it's not black magics, but it's just understanding that Q-learning is following the Bellman equation, which is kind of making good probability or good reward or bad reward diffuse a bit as if you were exploring a maze, while the policy gradient, you're taking a more like mathematical approach of trying to take some gradient of the value you get of the reward or the discounted reward directly from looking at the sensitivity to the policy. So now that this background and algorithm are a bit introduced, some examples about deep reinforcement learning for active flow control. So I think that the use of deep reinforcement learning is a very natural candidate for active flow control and turbulence control, because you need to both find and express a solution, because we don't really know a priori what is the optimal way to control a system. There are several works that suggest from typically 2019 on that it is a promising approach. Some works that I was involved in, some works by other group. In the following, I will mostly focus on the work I've been involved in, because it's the ones, of course, I know best and it's easier to work with. But you should, if you are interested in this, do a literature review, and you will see that other groups have reproduced or done things similar but slightly different to what I'm going to present. So there are now quite many groups working on this. So when we looked at this first, we thought, okay, we should take a simple case that is computationally cheap and that is emblematic of fluid mechanics, and we ended up taking this Turek benchmark, so basically 2D Karman vortex treats, and starting very easy and then increasing the complexity as time goes, right? But starting from a case that's easy so that we understand a bit how it works. So basically, how do we use reinforcement learning to control this case? Well, we have the CFD itself that you can see here, and then we need an estimation of the state. So what kind of flow structures are present, and this is provided by the black dots, which are like probes of the flow. And then you need to act on the CFD. So this is done by two jets. So the red dots here, those are jets that blow perpendicularly to the surface of the cylinder at the top and bottom of the cylinder, and they are like synthetic jets. So what you blow at one jet, you suck in at the other and the opposite, so you don't do mass addition or removal. And then you also need to have a reward function, and in our case, the reward function is more or less just the drag, maybe penalizing a bit the lift fluctuations also. And when you couple this and you put it into this reinforcement learning framework, what you get basically is this. So at the top, you can see the case without any control, and at the bottom, you can see the case where you have been doing some control. So basically, you drastically reduce the vortex shedding. And really, like, there is nothing to do special as a user to get this. You just apply reinforcement learning and see what comes out of it. You can see the code is available on GitHub. Everything is available there. So CFD, the reinforcement learning, the scripts for training and evaluating, and so on. So if we try to do a bit of physics, what is happening? The small jet control, because the jets are quite small, we'll see, allow for doing a form of boat tailing, so basically elongating the recirculation bubble. And this leads to a reduction of the pressure drop in the wake, which leads to a reduction of the drag. So if you look at the drag coefficient, for example, in blue, you would have the case of the cylinder without actuation, and in black you can see what happens when you turn on the control, and you can see also the normalized mass flow rate blown by the jets. So you first have a bit of large control in order to change the state of the system, and then it's enough to just do small actuations to keep it there. How good is the strategy that we obtain? We obtain about 8% drag reduction, and then we can go in the literature and look a bit about control of this specific case. And the literature says to use that, okay, the drag coefficient in this case is the drag coefficient in the base flow plus the drag coefficient due to the vortex shedding. And in this case, you can probably only control the vortex shedding part of it. So how big is the CD due to shedding and versus the CD due to the base flow. You can do a simulation when you force the flow to be stable, for example, by, in this specific case, simulating only half the domain, and you can get the values of both of these. And when we look into this, we find out that the reinforcement learning is suppressing 93% of the vortex shedding induced drag. So we're very close to having an optimal policy that completely negates the effect of this vortex shedding. Okay, so this was a really first work we did, and actually it was very straightforward and easy to do this. Like once we had understood a bit how to use a library, it took maybe only 1 week or so to do this work. It took more time to write it down in a paper. But once we have done this, I think the key question is to go higher up in complexity and Reynolds number, increasing the dimensionality of the control space, looking at more challenging configuration and so on. So this is what I will walk you through quickly now. So the first thing we wanted to do is, okay, if we want to look at more challenging cases, then we need to be able to train faster. And how to train faster? Well, about 99.9% of the CPU time is used by the CFD, not the reinforcement learning, because we actually use the reinforcement learning doesn't need a very complex artificial neural network, and yeah, the CFD is expensive, as we know. So the best thing we can do to go faster is to be able to collect more experiences faster. We don't need to try to optimize the reinforcement learning per se. And there are 2 directions. Of course, we can parallelize the CFD simulations, but we know how this can be challenging and stuff like this. The other thing is that reinforcement learning is an algorithm that is naturally parallel, because when you want to do the update of the Q function or the policy, you want to do it based on several trajectories, and those trajectories are independent of each other, so you can just gather them in parallel. And this is exactly what we illustrated here, that we can gather these trajectories in the phase space, so interaction with the system in parallel, and then we can get a perfect speed up due to the setup of the reinforcement learning by, for example, a factor up to 60. But the more complex your system, the more environments you can use in parallel to have speed up. When we do this, then we can start to look at more complex cases, so still playing in 2D to understand a bit and get experience. For example, we had this work in 2020 when we look at controlling up to Reynolds 400, and in addition, we don't just train the reinforcement learning on controlling 1 Reynolds number, but we train it on controlling several Reynolds number. And we find out that we can, in the end, get a reinforcement learning agent that is able to control well over the full range of Reynolds number we're considering. So you can see in blue the drag you would get without control. In black, the optimal case you would get if you suppressed the full vortex shedding part. And then in orange, the drag you get by applying the reinforcement learning trained over this range of Reynolds number. And it's actually follows generally the trend of the theory. It's a bit less good at the lower Reynolds number and a bit better at the higher Reynolds number. And it's of course because this theory, it's not exact in a sense. It's just saying that typically you should be able to suppress the vortex shedding part. But yeah, you can. It's hard to do as good at lower Reynolds number, and when you go a bit higher Reynolds number, you can actually do a bit better. So same thing here. If you have any questions about how it's done in details, the code is available on GitHub. We can try to push the Reynolds number even further. So we had a case where we start to look at 2D Reynolds number 1000. So of course, when we look at 2D case and we look at higher Reynolds number, we are not looking at something that is perfectly the physics you would obtain, because there would be a point where your flow gets to be 3D. But to start to understand how it is to interact with those stochastic nonlinear systems, I still think it's interesting to look at 2D cases. And there is a point where we will have to say, okay, now we're finished looking at 2D and we'll look at 3D. And I think we've come to this point. But we took the liberty to look at higher and higher Reynolds number in 2D. So basically, if we go to Reynolds number 1000, then we start to have some chaotic kind of 2D pseudo turbulence, and we find the same kind of thing. I mean, you cannot really stabilize the flow or get a clean, nice pattern. It will always be a bit messy, but you still get quite a lot of drag reduction, up to about, for example, 30% by applying the trained DRL control. So you're still able to interact with your flow, even if it's like chaotic or pseudo-turbulent or something. So the highest Reynolds number we've done in 2D, and I think we're finished now looking at 2D because we should go to 3D to get those more realistic effects, is Reynolds number 2000. And what was interesting here is that we find out that the reinforcement learning, instead of doing basically wake opposition control, as it was doing in the previous cases, is starting to use a completely different strategy at this Reynolds number, which is energizing the boundary layer at the top and bottom of the cylinder. So you can see it here. This is the development of the simulation without control first, and then now the control is switched on, and you see you don't really see jets that are doing wake opposition control, but you can rather see all these small vorticity structures coming from the edge of the cylinder, and this is because the jets are energizing the boundary layer to kind of trigger a form of drag crisis. I can show it again. We start from the base, so we start from the state of rest. It has to converge a bit. There you get the unactuated, uncontrolled vortex shedding, and now the control is switched on, and you can see how this changes a lot the nature of the wake. So probably for somebody who is familiar with the physics, it's not very surprising that at some point you want to shift from a wake opposition control to a boundary layer energization / triggering of the drag crisis. But I think it's very interesting to see that it's what you actually get when you put the reinforcement learning at work on this case. Okay, so far we've been looking at 2D cases, and it's convenient because there are relatively few inputs and outputs. But if we want to go into 3D, then we will need to be able to have typically many more outputs, right? Because it's not enough to just have 2 jets. You will need many jets across a cylinder, or if you look at the boundary layer, you will need to be able to control it at the wall at many places. And this thing of having reinforcement learning applying a control at many different points is a tiny bit tricky if you don't do it the right way. So we actually started to discuss this first in this paper here. And the example we take is not the important thing. The important thing is the methodology and what we illustrate about reinforcement learning. But basically, the case we're looking at is this thin fluid falling flow. So basically, you have an inclined plate and you have a thin fluid film falling on it, and this creates ripples, get unstable, and so on and so on. And we just try to control those ripples. Same thing, all the code is available here. So the naive way of doing it would just be to say, okay, that's very great. We have this falling plane. We need to put quite many actuators because even if you control well at one place, it will always get destabilized later down. And then around each of these actuators, you put some sensors and you define a global reward, and you put all of this into a neural network. So then you end up with a neural network that is reading n input and doing n output and having one reward value. But actually, if you think a tiny bit about this, the curse of dimensionality is going to bite you on this one. Because for a thought experiment, let's say that you have p possible jet trances. So you basically discretize the jet output. And you have n jets, so n control locations controlled by your neural network. Then in order to fully explore the combination of all these different jets, you will need typically at least something like p to the power of n combination. And this is something that is far too expensive to explore as n goes to 5, 10, 20, or 100. The good thing is that, of course, we can be a bit smart and do something better. So first thing we can do better is we can say, okay, we want to apply the same policy everywhere because the equation system is the same, the physics is the same, and kind of the physics are invariant. And this can be easily done by using a convolutional neural network, which is basically applying the same kernel and the same transformation on all inputs. So this is what we call the method M2. We could just still say we gather all observations and produce all actions at the same time. but this time we use a neural network that by construction enforces the use of the same policy everywhere. So taking advantage of the translational invariance of the physics. But here you can note that it's much better in a sense because we don't need to relearn the same thing at different locations, but at the same time, you don't really exploit the reward value very well because you still gather all the reward and kind of average it or sum it. It means if you do something very good at jet number 1 and something very bad at jet number 3, you will just get a reward that's average instead of knowing that you actually were doing good somewhere and bad somewhere. So then we can define this method M3 instead, which is saying, okay, we want not only to apply the same policy everywhere on the system, but in addition, we want to make the agent, so the reinforcement learning, aware of where it's doing good and where it's doing bad during the training. And for this, what we say is that, okay, we have the CFD, which is traditionally seen as the environment you try to control, but we will kind of virtually split this environment into several local environments, and we'll actually try to control each of those local environments with a reinforcement learning agent. But to take advantage of the fact that the physics is invariant, we will enforce that all these reinforcement learning agents we apply on different locations of the CFD are using the same neural network and the same weights and the same policy. So this way we have kind of a self-collaborative strategy. We say the best way to control this system is to split it into several smaller control and then to apply the same reinforcement learning on all of them, sharing their experience and working together. Just to illustrate a tiny bit, if we go, so in color you will see the method M1, M2, and M3. You will see in X the number of steps you need to learn and the reward on the Y-axis. And this is trying to control with 1 jet, 5 jets, 10 jets, and 20 jets, going from left to right, top to bottom. And what you can see is that, of course, when you have only 1 jet, all those methods are equivalent. You could think about it a bit and convince you of this. But as you increase the number of jets, the method M3 remains very good because it's able to handle all these jets independently and still learn the physics. But the methods M1 and M2 get worse and worse. So this is really the illustration that this multi-agent reinforcement learning is critical to get it to work. And a small note here, depending on how you plot, it may look like you need many more actions in order to be able to learn with the method M3. So this is showing the cost of learning for the method M3. But what you have to remember is that since we have split the environment, in the case of the method M3, each time you do 1 CFD step, you get actually like 20 examples if you have 20 jets, or 10 examples if you have 10 jets. So, and the reinforcement learning is very cheap. The expensive thing is the CFD. So if you actually show the reward evolution as a function of the CFD steps, then you see that all of these things collapse, which is really good and intuitive because it means that you're able to learn the physics independently of the number of jets for the same time by splitting it this way. So basically, this is the kind of thing you need to be able to go to systems where you have very many controls to apply. And I think that the first examples are starting to come now. So there was a preprint last year. We have a paper that's accepted with minor revision about looking, for example, at the turbulent channel flow control. So basically, we have a turbulent channel that is turbulent, that can be a minimal channel or a full channel. And we apply wall suction or blowing at the lower wall with a 0 net mass flow rate. And the goal is to minimize the drag or the friction Reynolds number. And we apply this multi-agent reinforcement learning and compare to opposition control from the literature. Again, if you have questions, all the code is available here. So basically, when we do this on the minimal channel first, because we first train again this minimal channel, you can see the opposition control typically and the reinforcement learning. All of these curves, they have uncertainty bars because this is stochastic. So if you do different repeats, you will get different values. And in the case without control, if you look at this, what's the name of it again? diagnostic plot, you can see that there are some sweeps and ejections. So basically, there is quite a lot of dynamics happening. So opposition control reduces it a bit, but you still have quite a lot of it happening. And if you look at the deep reinforcement learning, then you see that really the physics of the flow are changed and you lose all the sweeps and ejections, which also corresponds to your improvement in drag reduction compared to the opposition control. We can also take those results that are trained in the minimal channel and apply them in the full channel, and then we get more or less the same. There is still a tiny bit of sweeps and ejection left, even when you control with the reinforcement learning though. And we are in the process of looking, is it because the channels physics are a bit different, and or is it because we train in a minimal channel and apply in a full channel? So we should do a bit of retraining. Maybe maybe a combination of both, but still the conclusion is still that we are able to significantly improve upon opposition control. Okay, so time for the conclusion. Reinforcement learning is, in my opinion, a promising avenue for active flow control. And I mean, I say my opinion, but there are many other people who look at it too. And fundamentally, exploration in a reinforcement learning-like way may be the only approach that is possible with complex nonlinear high dimensionality systems, because you really have to explore your system by trial and error to learn its structure. There have been a number of recent results about proofs of concept, parallelization, getting speed-ups, getting robust control, applying to large systems with invariance, so this M3 method. And what we are doing, I think, as a community, is that we are patiently building up cases and examples and increasing complexity and going to more and more 3D complex realistic systems, increasing the Reynolds number and so on. So I think what is happening now is very exciting. We don't really know how far it will be able to go. Like, will we meet a limit and not be able to apply it any longer when we increase complexity, or will we always be able to apply it as long as we have enough computational powers? All of this is kind of open questions that we are investigating, not only myself, but many groups in the community. And a few words about this, I really think that it's important to share the code and the implementations to speed up the progress, make everything reproducible, and help groups like understand what each other is doing and split tasks in a sense. I have one last slide just to say that I've been focusing on reinforcement learning, but conceptually there are also other methods that works a bit in the same way. So for example, Bernard Noack and people around him have been looking at genetic programming for a long time. And genetic programming is kind of trying also to solve this problem in a data-driven way, using different classes of algorithms. So will it work less good, better, similarly? Don't know, but yeah, the future will tell us. Yes, that was everything. Is there any questions?
Fantastic. Thank you so much, Jean, for your talk. We do have time for questions. So if you are in the audience and you'd like to ask a question, you can just unmute yourself and ask away, or you can pop your question in the chat, or you can also put your hand up in the participants list and I can call upon you, whatever is easiest. While people are just gathering their thoughts, I might ask a quick question. So right at the end, when you were talking about going to 3D, and one of the things that you mentioned was splitting into several local environments. So what are the drawbacks to this? Like, are there any drawbacks? Are there any negatives with this? Like, will you potentially miss some of the physics, some of the, I don't know, the large scale physics in this, or should we not really worry about that too much?
So I don't think we will lose any of the physics, because like kind of the fact that we follow the physics is enforced by the fact that we have a CFD simulation. What can happen is that we have one system we try to optimize, and we say it would be too difficult to optimize it as a whole by exploration. So instead, we will try to optimize it locally and use some properties of your system, like some form of invariance of the physics, in order to be more effective at doing it. So of course, there is a risk that by applying this system, we end up doing local optimization at the side of each other instead of a global optimization, and maybe we converge to an optimum that is less good. But in order to mitigate this, what we can do is that, for example, the reward that we give to the local agents, it's not just the local reward, but it can be, for example, 0.8 times the local reward plus 0.2 times the global reward. So we get the agent an incitement to kind of cooperate and also optimize the system as a whole. Yeah.
Oh, that's a good point. Yeah, that you can split up the reward and weight it towards the local or the global. That makes sense.
And it's just one of the tricks we use, but maybe people can think about other more efficient tricks. So, and the other thing is, I also think it depends a lot on what system you look at, because sometimes you have systems with really long distance correlations, and then it may be challenging to get really the best optimal by using this method. And all the time you have a big systems, but there are actually many different blobs that don't interact so much between them. Like, for example, if you take Rayleigh-Bernard convection in 3D, you have many cells developing and probably two cells that are very far away from each other. They don't have so much to say. If not, you manage to make them coalesce, for example. So in this case, I think it's quite likely that this M3 method will work well.
Thank you. We have a question in the chat. I'll read that out for the video recording. So the question is, have you tried to look at the dynamics of a three-dimensional bluff body, a 3D wake, and try to implement active flow control using DRL?
Yes, so we're working on it now. There is actually an experimental study where people have looked at it already. Dixia Farnet all, they have a paper from a year or a year and a half ago. So, but they looked at a kind of simplified setup in an experiment. So basically you have a cylinder and then you have two small cylinder back and you can rotate the small cylinders. What happens then is that, of course, you get only a control that is the same over the full length of the big cylinder. So you don't manage to interact with kind of the 3D structures in a way that is dependent on where on the cylinder you are. But what they were doing was able to work quite well. I mean, it's maybe not so surprising, right? Because you can just rotate the small cylinders that are behind the main cylinder to kind of reattach the wake. And then you add a bit of fluctuation on top of it to avoid like big wobbling of the wake behind. But in our group now, we are working on the this thing first in numerical simulation, and maybe in experiment at some point, where we really take the cylinder and then we put jets, pairs of jets at different height on the cylinder, and then controlling them separately. And now the setup is already working quite well in simple cases, and we are going to higher Reynolds number. So we start to have like a 3D structure in the wake to see what happens. So we are working on it. And if I was to do this presentation in half a year, there would probably be some extra slides about it.
Great, thank you for answering that question. Any other questions coming from the audience? Oh, the person who asked the question said, thank you very much for the answer as well.
My pleasure.
I have one more question, but it's very, I don't know, it's a little bit speculative. So sorry about this one. But I was interested, obviously what you're doing now, it's all about numerical simulations, but a lot of these active flow cases, like is the end game eventually maybe to test this in an actual lab and seeing if, you know, a real size like lab experiment could do something with these jets and actually control the flow in the same way as a numerical simulation? And how far away is that? Is that really far away, or is that only like very close?
So that would really be the end game, no doubt about this. There are already some groups that have been looking at it, like this example with the cylinders. Even if they were not using jets, they were using another method. You know, the challenge is that I'm just one person doing it on the side of my main work activity, so it would be difficult for me to set up an experiment. Maybe some of the people I collaborate with may set up some experiment in the future, or some other groups that I don't know of. But it should be very much applicable to real-world experiment, because all those techniques, they come a bit from machine learning and robotics, and that's exactly what they do, right? They build the robot and they apply it on the robot. So it's perfectly doable. And I even think that as you go for higher Reynolds number, it would be more and more attractive to do it even directly in experiments, because you can both train and evaluate in experiments rather than in simulation. Because as you go to higher Reynolds number, it would be super expensive to simulate, but kind of the cost of running your analog simulation, which is a real world, remains low. And it's even like if you increase your Reynolds number by increasing speed, you can actually gather more examples by unit times as you increase the Reynolds numbers. And so there is some good scaling. In the world of other methods of control, like genetic programming, the group of Bernard et al., they are a very big and nice group doing a lot of exciting things, and they have been applying some genetic programming control to many cases with success. So I believe that maybe reinforcement learning has advantages compared to genetic programming, but maybe I'm wrong, or maybe people would disagree. But I think the fact that they can make it work with genetic programming is a strong indication that we can make it work with reinforcement learning too.
Fantastic. Thank you. It sounds like a very interesting and very dynamic field at the moment. All right. So any last questions for our speaker? Okay, so if not, I'll call the seminar to a close and thank our speaker once again. And hopefully we'll see some of you. I think we have another seminar on next week at the same time. So potentially see some of you in that one too. Right, thanks.
Thank you very much.